Okay, so we are happy to have Ghislain Fourier today. Let's start. Ghislain, please.
Yeah, thanks for the invitation. And so I'm going to talk about PBW degenerations. And this is like, I mean, there will be probably no audience ever having more experts in than today. This is joint work with Rocco Kirivi and Xin Fang, and at least I've seen Xin in the audience, but I think Rocco will also come. He promised. So if you have any question, just ask my co-authors. Yeah. Just to bring everyone on the same page, I would just say what's the PBW filtration and what we want to discuss. I mean, someone like this PBW filtration and degeneration framework started more than 10 years ago, and it's still growing, and we have more and more applications and see connections somewhere. But still it's like you play with your toy example and you figure out there's a nice property for your toy example, and then you want to know whether this is very special about your toy example or whether you can find this property somewhere else. And the property I want to discuss today is like, if you take a PBW degeneration of a variety or module, doesn't matter, in the SLN case, then you can find this module as a de Mazur module or the variety as a Schubert variety. And now the question is, how does this generalize to other types, or maybe itself to de Mazur modules? So the question is how does this generalizes, and is this something very special about SLN? Yeah. And if this is something special about SLN, how far can we degenerate to have still such a nice property? Yeah, so this is the picture of today. So let me just give you the introduction. And so so let G be any Lie algebra, be any let's say it doesn't matter, but we can say it's finite dimensional Lie algebra, let's say over C, but also this doesn't matter in the beginning. And then U of G is the universal enveloping algebra. And then we define a filtration on this universal enveloping algebra, namely we say UGS, this is defined to be the span of xi1, xil with xij in G and L lesser equals to S. And this is supposed to be just the C span of this. So we just take, we have the universal enveloping algebra, and we know a basis of this. That's the PBW theorem. And so we take the span of all monomials of degree lesser equals to S. This certainly gives you a filtration. And the PBW theorem, if you want to give it another formulation for the PBW theorem, then so Poincaré, Birkhoff, Witt, it says that if you take from this filtration the universal enveloping algebra, the associated graded algebra, then this is isomorphic to just the symmetric algebra in G. And actually now, and this becomes important here, we want to consider this in a slightly different way. You know, you have if the universal enveloping algebra is symmetric, then this means that, oh yeah, this is a universal enveloping algebra of an abelian Lie algebra. So this is actually nothing else but you take the same space, so you still take your vector space G, but with a trivial Lie bracket. And then you take the universal enveloping algebra, and this is exactly our associated graded algebra. So and now we have this for the algebra, and now we want to consider the induced modules. So let V be a cyclic U of G module with generator say V, and then we define here a filtration. Vs is just defined to be U G as applied on my generator. And again, this is a filtration of my module. I can take the associated graded, and so I can consider the associated graded module of this. This is just Vs by Vs minus 1, s greater equal to 0. And the trick here is that the associated graded module is of course a module for the associated graded algebra. Yeah, so this one is a module, and it's still a cyclic module because the generator stays a module for U of G, and as we just said, this is nothing but the universal enveloping algebra of an abelian algebra. And this is basically the setup we are considering. So this is something very, very classical. I mean, this is like, it's around in Lie theory for 100 years. Yeah, as long as you have something on the universal enveloping algebra. And of course, we don't want to consider this in this full generality, but we are going down to a little bit more special situation. Namely, we say, so let G be in the following always a semi-simple Lie algebra, and we consider the following decomposition. Yeah, so this should be finite dimensional and semi-simple over C. Yeah, so I'm not putting a minus to the n because I will use the n everywhere else, and the minus will just disturb us. Yeah? So there's an n plus h and n, and so lambda should be just a dominant integral rate, and v lambda the finite dimensional G module of highest weight lambda. Yeah, and we are fixing a generator here. This is important here. We're fixing a generator V lambda in V lambda of highest weight lambda. Make sure. So the PBW filtration on the algebra, it's just saying that, oh, the universal enveloping algebra is naturally filtered by this. But the associated graded module depends, of course, on the choice of your generator. I mean, if you take a simple module here, then you can take any non-zero vector, and this would be a generator. So the associated graded module depends on the chosen generator. And so this is why I have to say here, I'm fixing my highest weight generator in this setup. And then we all know that this V lambda is nothing but UN applied on V lambda. Yeah, so this is a highest weight vector. And if you apply UN on this, you get everything. And so now what we get here is then the previous says that if you take the associated graded module here, then this is a module for S of N. Yeah. So I don't need the rest of G to generate the module, but in fact there's more action on this. Yeah, and let's denote this one as VA lambda. Yeah, so the A stands here for we abelianize the action of we abelianize our Lie algebra, and that's the A for. But keep always in mind that VA lambda is always the associated graded of some V lambda. I should also note here already that later on this A will not be always abelian. Yeah, but let's don't bother with details already. So actually there's more on this, because in this special situation, if I'm taking the PBW filtration of this N, then this PBW filtration is stable under the action of N plus and H. Yeah, so there's more on this. Namely, there's like this proposition that VA lambda is a module for, and now this looks very strange. I'm taking B, so let's call this one here B. Yeah, this is our Borel subalgebra, and this is the semi-direct product with NA. I'm putting an A here. This is the abelianized version. And how does this look like? So I mean, the B still acts, the N plus acts on N minus just by the adjoint representation. And the only thing we are considering is whenever you hit something in H or N plus, this is just 0. Yeah, so you have a natural action of B on NA, and this VA lambda is a module for this. Yeah, so now you have a graded module, yeah, for the action of N. and the operators from B, they all have degree 0. That's the important thing here. So now the question is now, that's a very simple construction so far. We haven't done much. Yeah, so we just took a natural filtration, and we just took the associated graded module. But now the question is, so you know a lot of things about V lambda. Yeah, if you consider V lambda as your simple module for semi-simple Lie algebra, you know a lot. Like, I mean, of course, we can just start with dimension formulas, character formulas. They all stay the same. Because the H still acts on everything, but make sure you have a graded module. You should say something about the graded character. On the other hand, you know how to construct this V lambda. Yeah, you can construct the V lambda by just giving a defining ideal in the universal enveloping algebra, and we all know this defining ideal. Yeah, so there should be a highest weight vector. Yeah, and the only thing you ask for that this is integrable. So you know the defining relations. So again, you have something which is a highest weight vector, yeah, because B still acts on your generator by 0. So you can ask what's the defining idea. Yeah. You could also say, like, yeah, this V lambda, actually I can realize this V lambda in the tensor product of fundamental representations. Yeah, so you take your lambda, you write it as sum of fundamentals, and then you know V lambda sits inside the tensor product of fundamentals. Now you can ask, is there something similar here? What are the smallest pieces to construct all these modules? Does it still work? So you take just the tensor product of degenerations of fundamental modules, and you can ask, oh, is this VA lambda the Cartan component of this? So you can ask the very same question that you had that you have on V lambda, and where you know the result for V lambda for a long time. And then, of course, if you consider V lambda, then in the 50s, Gelfand and Zetlin, they constructed actually a basis for this space, and they actually gave the action of the elements from G. So now you can ask, so can you give another basis? While basis, of course, that's the same space, yeah, because it's only the associated graded, but I want to say basis in the sense of a monomial basis. So I want to give you monomials in UN such that if you act on the highest weight vector, this provides a basis. Yeah, so you ask for a monomial basis. And it turns out, of course, Gelfand Zetlin, this is, you can write down this as a monomial basis. And turns out this is not a basis for the space, because you go to the associated graded and something is just 0. So a basis of your space is a monomial basis for the algebra, for the module, is not necessarily monomial base for the associated graded. So you can ask what's the corresponding basis. Okay, and so let's start with the question about the idea, just to get a feeling for what's happening, and that we actually we have a lot of things that we can just translate. Yeah, so we already know that, so we call from whatever your Lie algebra lecture, yeah, that V lambda is nothing but U of G by some ideal I lambda. Yeah, so where lambda is in P plus. And what's this ideal? This ideal is generated by, yeah, so it should be a highest weight vector. So let me call the root vectors from n plus by E. It should be a weight vector, so H minus lambda of H should be just 0. And so far I'm just getting the Weber module, and now I want to make it integrable. So let me denote by F the root vectors from n minus, and then these are your defining relations. Yeah. And now it's clear that if you go to the associated graded, then the corresponding elements are still there as defining elements. So this implies that if you consider VA lambda, and now let's write it as a quotient of NA times V lambda, or if you want to say this is just, as I said a few times, like this, and then we ask for the defining idea. Yeah, so this is isomorphic to Sn by some ideal I lambda A, and we can ask, what's this ideal I lambda A? So I lambda A, so what's this ideal? And you definitely know that whatever x by 0 on v lambda, x by 0 on v lambda a. Yeah, so you can easily translate this, and you know what's acting by 0. So you can say, oh, inside here, I'm getting the idea generated by Sn on the set U of B acting on F alpha lambda on H alpha plus 1. Yeah, and this is for all alpha in phi plus the root. So these, you definitely know F alpha to lambda H alpha plus 1 is 0. And then, you know, this is a module for B as well. So this ideal is stable, and then you apply Sn on this. And the conjecture, yeah, and let's say this conjecture is maybe due to Yevgeny, or maybe to Yevgeny, Peter, and myself. And I think we never stated this conjecture anywhere. Yeah, but the conjecture is that this is an inequality. Yeah, so this is the defining ideal for I lambda A. Yeah, and okay, so now we can prove this in several cases. Yeah, but we want to also say that today I want to give like a way around this to prove this conjecture in various cases by identifying these modules with something different. Yeah, and namely with Demasur modules. So let us consider at least the SLN plus 1 case. Yeah, and for the SLN plus 1 case, we actually proved this conjecture. And how did we prove this conjecture? I mean, you have this ideal, and you want to say that this ideal is generated by these elements. So you have to show that these elements are enough to generate your ideal. So basically, you have to use these elements or the generators to reduce everything to show that everything is an I lambda A. Yeah, and so we actually did this by providing a new basis for V lambda, a new monomial basis for V lambda. And for this, I just introduced what is a Dieck path, and actually I don't want to write everything down, so I prepared this, and namely it's here. Yeah, so I have to say what is a Dieck path. Yeah, and so we consider GB SLN plus 1. Actually, the picture is from SL6. Yeah, and I'm writing down here the so this here is these are my negative roots. Actually, I'm just don't write down the minus sign. Yeah, and I'm arranging this as they sit inside a matrix realization of SLN plus 1. And now what is a Dieck path? A Dieck path is a path within this pattern that starts with a simple root, so with a root from the diagonal, and it ends with a simple root. Yeah, and the only condition that I'm asking is if you go along your path, you always have to go down or to the right, nothing else is allowed. Yeah, and then you see there are two examples. Yeah, so a path alpha 2, alpha 2, 3, alpha 3. Yeah, so this is this path that goes like this. Yeah. Another passage, you start here alpha 1, alpha 1, 2, alpha 1, 3, alpha 2, 3, alpha 2, 4, alpha 2, 5, alpha 3, 5, alpha 4, 5, alpha 5. Yeah, so this is another path, and you consider just a Dieck path is something that starts with alpha I and it ends with alpha I. Yeah, and in between you just go down and to the right. You can give a combinatorial formula saying that if you want to write down all the roots as alpha ij, this is just a sum from I to j, then a Dieck path is either increasing the j by 1 or the I by 1. That's a Dieck path. Yeah, and you want to start and end with simple roots. And now let's take a lambda, just some dominant integral weight. We can just write this in terms of our fundamental weights. So the omega i's are just fundamental weights here. And then I'm defining a polytope P lambda, and that's a polytope defined as follows. So all the entries are greater or equal to 0, and for all Dieck paths, so I'm just taking all possible Dieck paths in such a diagram. If you sum up, so the polytope lives in R to the number of positive roots. So every coordinate is indexed by a positive root. And the condition here is if you sum up the coordinates lying on a common Dieck path, then the sum has to be less or equal to mi plus and so on plus mj. So where's this I and j coming from? This is the beginning and the end of your deep pairs. That's a polytope. Yeah, and let's consider this as lambda as being just the lattice point in this polytope. And for every lattice point in this polytope, I can just associate a monomial. And I'm doing just exactly what one expects. So I know that the coordinates are labeled by positive roots. So I'm just taking the coordinate corresponding to alpha, taking the entry, and I'm just taking f alpha to x alpha. Yeah. And if I'm writing this as this is not a problem. It's certainly, this is an element in Sn minus. Yeah. I have to be a little bit more careful with un, because this is not commutative. So I have to say how to write down such a product, but it doesn't matter. You just fix any order. Yeah, it doesn't matter. Just choose your most favorite order among positive roots and just write it down. So this is an assignment of a lattice point to a monomial. And now the theorem that we proved, I think 2009, is that if you take all these monomials corresponding to lattice points in S lambda, and you apply on V lambda, then this is a basis for the associated graded space. And moreover, it's also, because you can always lift, it's also a basis for V lambda. And so this basis was conjectured by Wienberg, and I think he proved this for small rank cases. Yeah, and so we proved this conjecture, and now there is a basis which is compatible with the PBW degree. And this actually means that in some sense you have to be greedy. You have to take for every, if you want to write about basis, you have to choose a monomial of minimal possible PBW degree. So that's your example. So that's here's a basis, yeah, and from here you can even deduce the properties. So now here you have a monomial basis. So the other types, let's consider other types, yeah, and similar results also for the symplectic Lie algebra. Yeah, so you take sp2n, and the pattern looks very similar. You still have deep pairs. And then for G2, there's a basis, yeah, defined by Gornitsky. And of course, you cannot deal with deep pairs anymore, but this is a very nice basis. We see the properties later on. Yeah. And then there is and now we're already coming into the area where you cannot abelianize properly. Yeah, namely, if you consider the symplectic, the orthogonal SO2n plus 1. Yeah, then Igor Machlin, who's also here in the audience, or an organizer actually, gave you basis, but this is not a basis for VA lambda. It's a basis for something which is almost abelianized. Yeah, and so how to consider this PBW degeneration? It's saying like you take your n minus, so your n, and this is a Lie subalgebra, and it's not commutative. Yeah, so it's generated by root vectors for simple roots, and now you make all of this commutative, and that's NA. So you basically destroy your Lie action. So you can do this by saying like, oh, I've just asked that all my simple roots, the root vectors for simple roots, they commute. This is what I can ask, and this generates that everything is commutative. Now, in this particular case for type B, this is the odd orthogonal case. This doesn't work. So it's the basis that Igor provided works only if you say that my short root should not be abelian. Yeah? So the short root should not be abelian. So this is something that sits between n and your abelianized version. So it's something that is partially degenerated. Yeah, and in some sense, this is as far as you can or should go to still have very nice properties. Yeah, so we already see that we have a problem of getting a nice basis for Bn for the abelianized Lie algebra. Yeah, there is some for type B3 by Backhaus and Kusch, but it doesn't generalize to Bn. And then even more if you go to so I did it then later for in the SLN+1 case for some de Mazur modules. Yeah, not for all the Mazur modules, yeah, but again, I wrote down a monomial basis, and actually this was the basis was parameterized by just some phase of the previous polytope. Yeah, so you take this polytope P lambda, and whenever you have a particular de Mazur Y group element, let's call them triangular, then the basis is parameterized by a phase of your polytope. I'm not saying that you cannot do this outside. I'm not saying that you cannot do this outside for all de Mazur modules, yeah, outside of this triangular case. I'm not claiming this, yeah, but for the triangular case, this actually is very well behaved. Okay, so now there's something in common for all these bases, because we have now seen the SLN case, we have the SPN case, we have the orthogonal case, we have a G2 case. There's something similar that happens for all of them. And this is that this polytope or this S lambda is very well behaved. Yeah, and this is the following. So we consider the following. Let me find this. Yeah, yeah. So consider consider S, and this is, so I have to say, in all these cases that I mentioned here, there's always a polytope, and there's always the set of lattice points, and this will be always just some S lambda. Yeah, one has to say, be careful here with number 3. This is special. We come back to this later. Yeah, so we can just take the sum of all these S lambda, and we're just giving a weight, namely lambda, and lambda is in P plus, and then so this lives inside, so all of them are living inside R to the number of positive roots, yeah, times, and this is just R to the rank of G. Yeah, so this is like, I just want to take the lattice points in my polytope, and I want to attach the highest weight to make a formal sum of this. Then S is a semigroup. Yeah, and actually how to add on this. So this, like, I'm taking some X alpha lambda plus Y alpha mu, and this is nothing but X alpha plus Y plus X alpha plus Y alpha lambda plus mu. Yeah, so that's a group action. So this is a semigroup. And now the question is, so if this is a semigroup, if you consider the second coordinate here, this coordinate here, I mean, this is just the same as our previous P plus, the dominant integral weights. They also form a semigroup, and you know the generators for the semigroup, yeah, because every weight can be written as a linear combination of fundamental weights. So now the question is, what are the generators of your S? Yeah, so what are the generators of S? Yeah, of course. I mean, we know it. So the generators we need a lot. Yeah, because certainly there's in degree 0 for lambda equals 0, there's only one element. For a fundamental weight, which are the generators of my P plus, I already have all the elements from S omega I. Yeah, so at least they have to be generators. Now the question is whether these are all generators, whether I need more than just these generators. And the answer, which is basically the summary of all the previous results that I mentioned, is saying that theorem S is generated by the following set: S omega I times omega I, yeah, where omega I is fundamental. Now I have to be careful here. So yeah, before Igor raises his hand, first of all, for all previous types, but G being SO2n+1. Yeah, here you actually have to add 2 omega n. Yeah, yeah. So here need also S2 omega n times 2 omega n. Yeah. So this is I mean, this is a very interesting thing that for the Bn case, the orthogonal case, it's not enough to take just the fundamentals. Yeah, if you look at the at omega n, so then you see you can take just the sum of these two sets. Yeah. And this is not giving you S2 omega n. Yeah, it's clear here. Maybe you want to make it as a remark. If you take this, yeah, of course I have to. I should write it in a different way. Yeah, I should write it as if you take omega n, this plus S omega n, if you take this sits inside S2 omega n, 2 omega n. Yeah, but it's not the same. It's not enough. So there's something missing. Yeah, so this is not generated by fundamentals. Okay, but in general, so whenever this applies, yeah, you have the following property. Yeah, so this is basically number one, and if you want to say it's actually corollary, or maybe it's the proof, depending on your order, is that S lambda plus S mu. Let's forget about the second coordinate. This is S lambda plus mu. Wherever this makes sense. So as I just said, for the for type B, you have to be a little bit careful with this, but for the other one, this property is true. Yeah, this is the same statement as part one. Yeah, and we call this I don't know why we started to call this Minkowski property. Yeah, so this is what we call Minkowski property. Yeah, actually, I think the correct name would be integer decomposition property. Yeah, but yeah, so this is the if you look at the literature which is older than our results, then maybe this is referred to integer decomposition property. But we like to use it, call them Minkowski property, because it's the Minkowski sum of two sets of lattice points. Okay, so I have to say, so this theorem is actually an intermediate step of the previous constructions. Yeah, so the writing down that this is a basis in the various cases is actually proving this theorem. Yeah, and now this theorem is telling you the following, and this is the beauty. So this looks like, oh, this is some combinatorics. But it's more than this, because actually it tells you just have to compute your basis for fundamentals. And now if you have a basis for fundamentals, then, oh, this basis is giving you lattice points. And the statement is, if you take an arbitrary lambda, you write it as a sum of fundamentals. And for every fundamental, you have your lattice points, you sum them up, which on the monomial level is just multiplying two monomials and reordering. This gives you a base. So the only thing you have to compute is fundamentals. And we use this later. Yeah, this is a very nice, it gives you a reduction to, oh, I just have to compute fundamentals. And we use this reduction. Yeah, we use this reduction to answer one or two other further questions. Okay, so now here's the point about this PBW degeneration. In some sense, it's a very natural filtration. Yeah, you get this. I mean, we all learn in our Lie algebra lecture that this is a filtration. Unfortunately, if you apply this filtration, then you're basically leaving your Lie theory, because what's an abelian Lie algebra? It's not interesting in our setup, because an abelian Lie algebra doesn't give you something interesting. So in some sense, you start with something that you really like, namely maybe your semi-simple Lie algebra. And then you're destroying all your Lie theory and you're down to an abelian action. So where's the point? Yeah. So in some sense, you're leaving your Lie theory world, your Lie world, where maybe we all feel a little bit home. But then something magic happened. And this is like, so we wrote our paper. And then I think I wrote the paper on the muscle models. And I have seen this pattern, but it doesn't pop up in my mind. But here's some magic that actually happened. Namely, the magic is happening here. So here's a magical picture. Namely, I'm drawing it. It actually looks like the previous picture, but with one difference. I just stretched out the roots a little bit. Yeah. So this looks like my previous SL6 picture. Yeah. The simple roots are on the diagonal and the other roots are below. But if you look carefully, this lives inside SL10. And I'm just taking every second simple root. And I'm just taking in every line, every column, every second root. And why is this interesting? Because now let's take this lambda. Lambda is our summation mi omega I, some dominant integral rate. And I'm writing down this lambda tilde, which is just, I'm taking the same coefficient, but I'm taking different fundamental weights. So I'm shifting my fundamental weights. Whatever was M1, M2, M3, M4, M5 now gets the coefficient for omega 1, omega 3, omega 5, omega 7, omega 9. Yeah, so I'm shifting everything. And then I can again look at Diekpass in this. Yeah, I mean, the definition of Diekpass is very natural. I'm just starting with the simple root, I'm going down to the right, I'm getting a Diekpass. So again, I can define a polytope. And this polytope is, of course, isomorphic to my previous polytope, because the polytope doesn't know about names of roots. It doesn't care. Yeah, the polytope is just defined to be, here's a Diekpass and that's an inequality. Yeah, so the polytope I can write down here by considering, again, Diekpass is the same as before. It's the very same. And especially, it's actually a phase of my previous polytope for SL10. So I'm just going into SL10, taking my polytope in here, and I'm just projecting down all the roots that do not appear in this picture to 0. All the coordinates are 0. And what is remaining is exactly my polytope. Yeah, so it's actually a phase of my previous polytope. And this is, I just said, the Marceau modules can be parameterized by phases of the previous polytope. Unfortunately, I haven't seen this. But this picture, so there is something beautiful about this. And Giovanni Irelli and Martina Lernini actually saw this picture from a geometric point of view. If you want to talk about quiver cross minus a realization. But in our term, in our language that I'm using today, here's the picture. Because what I did is, if I'm taking all the roots that appear in here, they form a subalgebra. Yeah, so the commutators are in. Why? Because the commutators are all 0. This is an abelian algebra, what's written here. That's an abelian algebra. And within this abelian algebra, I can write down again a monomial basis that monomials that actually look like the previous monomials. I'm just shifting all the roots. So the idea here is, here I'm starting with my SLN. I'm abelianizing within the SLN, but unfortunately, abelianizing means I'm destroying all Lie theory. But here's something, I recover whatever I did, it's still there, and I haven't destroyed any structure. This is by construction, this is abelian. From the very nature, I haven't destroyed anything. This just lives inside some SL10. And of course, this generalizes. Yeah, so if I can just do the for SLN and going into SL2n minus 1. And here's the beauty about this. Yeah, because so far I just write down some set of roots. Who cares? I mean, you can always do this. But this set of roots is very particular. This is special in this following sense, that we take tau. Tau is a Y group element, and it looks like you have to always read from right to left, yeah, to recognize the structure. Yeah, there's S1, then there's 3, 2, 3, 4, 5, 4, 5, 6, 7, and so on. Yeah, so this is a Y group element, and I'm continuing until I'm ending up in S2n minus 2. Yeah, and now I'm taking this Y group element and applying this the inverse to phi plus. Yeah, and this is now this phi plus is of S2n minus 2. Yeah, and if I'm acting on all positive roots, then I'm getting the two sets. Yeah, so these are negative roots and these are positive roots. Actually, these negative roots that I'm writing down here, these are exactly these roots. Yeah, and the positive roots I'm writing down here. And now this is the beauty. The positive roots are actually the differences between negative roots. Yeah, so in some sense, you look at all these negative roots and you look at the various differences. And now the positive roots that are staying here are actually the differences of these negative roots. Now, which actually translated in our picture, they acting by differential operators. So the positive roots are acting by differential operators on the negative roots. Yeah, so this set of negative root is stable under this. And that's basically the entire game. That's now you know the rule of the game. Namely, I actually found this set as in subalgebra with some extra operators which are stabilizing this set. But not only stabilizing, but I can go from one root to the other using differential operators. And this is exactly what we used in our original paper about the basis for SLN. We just needed this. We needed differential operators. In our original paper, we got them for free because you just took the V action. Now you're not getting this for free. You have to actually use this particular thing. So now we define a Lie algebra G tau to be just the direct sum of all these root spaces and H. And this sits inside SL2n minus 2. And then I'm taking my lambda and P. So this should be yeah. So this P triddle plus this is the dominant integral weights of SL2n minus 2, and I'm considering the de Mazur module for this lambda. So what's the de Mazur module? By definition, this is just U of B, so applied on V tau lambda. And that's my de Mazur module. And I don't like to consider de Mazur module as being an extreme weight module for a particular reason. So I just explained in a minute. So I like to twist my de Mazur modules a little bit. Yeah, namely I'm twisting this by tau inverse, so it gets a highest weight module. A de Mazur module is generated by U of B. Yeah. But I don't like this. So I'm twisting everything so it's a highest weight module. Now it's not a module anymore for U of B because this X trivial, but it's a module actually for this Lie algebra. Yeah, that's just the twist. Yeah, this is exactly tau inverse of positive roots is this. So now my de Mazur module is a module for G tau. And actually it's a submodule, of course, in V lambda. But, and that's the important thing, why I'm doing this is because now the associated graded module of the de Mazur module is a submodule of VA mu. Yeah, so this is why I'm turning this. It doesn't make sense. So you take the associated gradient, and as I just said in the beginning, yeah, it depends on your generator. Yeah, and now if I'm taking the V lambda, it's generated by my highest weight vector, and I'm taking my de Mazur module generated by extreme weight vectors. There's no sense of comparing filtrations. Yeah, they have different generators in different spaces. I want to compare these filtrations. And actually, if you twist, then the twisted de Mazur module is actually a submodule in the associated gradient. So the associated gradient of the twisted de Mazur module is a submodule in the associated gradient. It has nothing to do with de Mazur module. It just applies to all Lie algebras. You take A is Lie subalgebra in B, you take a cyclic module for B, you take the associated gradient module, you take the same generator for A, you take the subalgebra, it's always compatible. Yeah, that's basically PBW theorem. And so, but I want to use this because now I can compare easily my modules. Yeah, because what is nice about the de Mazur module? De Mazur module, I mean, this is again classical stuff. You have defining idea for a de Mazur module. You have character formulas. You have a defining idea. You have a lot of things for de Mazur module. And so I know if you take a de Mazur module, the set here that I wrote down here, this is the defining ideal for a de Mazur module as a module for G tau. Yeah, so it's actually, you see, this is just a subset of the generators that I used for V lambda. But I know now the Mazur module, the defining idea for the Mazur modules. And now the theorem by Cerulli, Irelli, Lanini, and then it was generalized with Wittleman is the following. First of all, the Lie algebra G tau, there should be a tau, not a W. Yeah, so the Lie algebra G tau is isomorphic to our degenerated algebra. Yeah, so this is what I explained. So you have the abelianized version. So you have here the abelianized version, and you have your differential operators, and that's an isomorphism as Lie algebras. And moreover, you have an isomorphism. The associated graded module is a de Mazur module for this particular tau. Yeah, of course, you have to shift lambda to lambda twiddle, but then it's a de Mazur module for this particular tau. Tau, not W. Yeah. So, and in some sense, this is telling you, yeah, you destroyed your Lie theory, but somehow like there's a magic stick and it tells you, no, not really. Not really. There's still, it's still a de Mazur module, and de Mazur module, this is, you still have your Lie theory. Okay, so now this is our this is what we want to find in different places, because this is a statement for SLN. Yeah, and let's just have a quick look at the proof, because this is all we need to actually generalize. Yeah, so let's have a look at the proof, and then we see what ingredients we need to generalize the proof to other types. Yeah, so let's consider the proof. Yeah, so proof idea, and it's not, I have to say, it's not really the idea that is written in Cerulli, Irelli, and Lanini, and the sequel with Peter Littleman, but it's what we need from here. Yeah, so the very first paper by Cerulli, Irelli, and Lanini is they just look at subspace. They really consider Quiver-Goswami and the linear algebra realization of the degenerate flag variety and compared to Schubert varieties. This is not what we're doing. We're doing the following. So we're using one or two properties that we proved in the last 10 years. So let V and W be cyclic modules with generators V and W, and then this one is the submodule in V tensor W generated by the tensor product of your generators. Yeah. Okay. And now this is a little bit too general. Yeah, for our particular case. Yeah, for highest weight modules, we fix highest weight vectors. So I don't want to do it in general. Just fix my highest weight vectors. So and this guy here, this one here is then the Cartan component. Yeah. So I just give just a notion for the Cartan component, and then here's something particularly interesting. Let lambda mu be in P plus. Yeah, same as in Lie algebra, and W in the Y group. Then first you have an isomorphism to the Cartan component. Yeah, so the Cartan component of V of the de Mazur module to lambda and mu is isomorphic to the de Mazur module for lambda plus mu. That's just classical. You just choose your embedding and it works. But actually, it's if you take the abelianized version, that's a different story. Yeah, so there's no point why this should be true in the abelian version, and this is actually this is the thing that we cannot answer whether this is they are isomorphic. Yeah, we can give one answer, and the answer that we can give is the following. Namely, if you take the Cartan component of this and you abelianize this, the Cartan component this is the de Mazur module, then this surjects onto Cartan component of the degenerations. Yeah, so this is, we proved this with Yevgeny Fagin and Peter Littleman in, I think, a paper called Favorable Modules. Yeah, so you have a surjection, and the pity is having this, this being an isomorphism would actually help a lot. Yeah, so having this in isomorphism would actually help you a lot, but in general it's not. Yeah, so at least you don't see that this is true. So one has to be careful a little bit here, because in some sense the result by Igor, for example, you know, if you take the result of Igor in the Bn case, then you can say, yeah, I'm just taking lambda mu to be my omega n, and take W, whatever, longest variable m. So I'm just writing down the statement for the simple modules. Then the question is whether the Cartan component of the tensor product, which is then V2 omega n, yeah, is on the left side. So I'm talking this one here would be in this case V of 2 omega n. On the other hand, and the degeneration of this, on the other hand, you have the tensor product of V omega n, the degeneration of V omega n with itself. And now is this map an isomorphism? So if in Igor's basis you would have the Minkowski property for fundamentals, then this would be an isomorphism. But is this an isomorphism? We cannot prove it using basis. Yeah. But in general, so can we describe what are the situations where this is wrong? Yeah. So this is a particular nice property, and we cannot prove this in general. Yeah. Okay. So, but we want to use this. Yeah. So I just said we are about to prove the theorem, or at least give the idea of the proof, and we want to use this property. These two properties actually. Now it's basically, maybe you see it already where this heads to. Namely, now, so you have to do. You actually have to work at some point. Yeah. So proof.
I'm sorry. May I ask a question?
Yeah.
So in your point 2, suppose we have lambda equal to mu. So are there counterexamples in this case? Actually
not, and I think this is true for lambda. So I'm not sure. I think it should be true in some sense, because I think, so I'm discussing this with Xin, but I think they will be always generated by V lambda. So it's only a problem if you do like multi-homogeneous in so with different weights.
Okay.
Yeah? But I think you in some sense, you know, so the idea basically is something like, you know, this is true for SLN.
Do we?
Oh no, this statement is no, if you don't, oh, so forget about W. So not the Mazur modules, but just simple.
No, for with no W, it's clear true, yeah.
But even then, if you take W, this is a sub-Lie algebra inside SLN.
Okay.
And so you can realize, in some sense, I want to boil this down to the fact that the semi group is generated by degree 1 always. Yeah? But as we already know, it's not true for Bn. So it's a matter of whether the coordinate ring of the associated variety is generated by degree 1, which is a weaker statement. Yeah, and you know, this statement is definitely true for SLN, and all the other ones can be realized as sub-Lie algebras inside SLN.
Ghislain, may I clarify?
Yeah.
So are you saying that you can prove that for any W for SLN, this is an isomorphism?
Let's see.
But it's not.
It will not. It will not. So
it is not generated by degree 1.
Exactly. Yeah.
You mean
Ego has a counterexample.
Yeah.
If lambda is mu, right?
If lambda is equal to mu.
Yeah. This is the question.
No, this is a different story. No. That's the point. So if lambda is not equal to mu, then ego has a counterexample.
Yeah. I'm asking about the equal.
And I think the other one is see, the idea is, so in some sense, to say that you want to realize everything inside some SLN, yeah, and then yeah, maybe we can talk afterwards, yeah, because it might take some time.
Sure, absolutely.
Yeah, but yeah, so yeah, it
sure,
looks
no.
like this could be just true in general, yeah. Yeah, but maybe let's skip this to afterwards, yeah.
Sure.
Okay, so now how do we want to use this proof? So you prove the statement that in the theorem, just prove the theorem, yeah. Maybe just because maybe now it's some time ago. So we want to prove it's here. We want to prove this theorem, yeah, that we have an isomorphism here. And so how to prove this? Prove the theorem for fundamentals. And I don't see any way how to avoid getting your hands dirty and prove this for fundamentals. But fundamentals, that's in general, fundamentals should be easy to prove. So now here's the picture. So you know that so then fix your W, yeah, fix your lambda, and this implies your lambda triple, yeah. Sorry, this should be a tau, yeah. This gives you a lambda triple, and then you write lambda as omega I1 plus omega IS, sum of fundamentals, and then you know that this lambda triple, yeah, there's still a tau here. This sits inside this Cartan component. Yeah, so we know this. This is just the previous statement. And now I proved this theorem already for fundamentals. I made my hands dirty, so I know this is isomorphic to the abelianized of this one. Yeah. So, and now inside here I have a Cartan component. Unfortunately, that's exactly our statement. We want that this Cartan component is the correct one. Yeah. So inside here, you have a Cartan component. Yeah. So this is the Cartan component, VA omega I1 Cartan component, V omega IS A. And I mean, all these maps are now maps for B and A, because we already have this isomorphism for the Lie algebras. Yeah, that's the easier part. And so this is an isomorphism, yeah, because this is just the Cartan component of the very same space. Yeah. So now what is missing is here. So here I know what I have is I have a surjective map onto this. Yeah, this is exactly what's written here. The first statement is the first line, and the second statement is this map. And I need this map to be an isomorphism. And then I have this isomorphism. So how to prove that this is an isomorphism? You can just compare dimensions. Yeah, or you prove that this is actually an isomorphism, and the rest is Minkowski property. And the Minkowski property is telling you that's an isomorphism. Yeah, it's basically comparing dimension, because the Minkowski property is more than just comparing points. It basically tells you this is the important thing, that if you take two bases, so you take monomials that correspond to two lattice points, then the sum is again a monomial that corresponds to a lattice point for the Cartan component, and this is what you're using here. And that's it. So this is where the Minkowski property comes into the picture. And now you know what we want to do. We want to generalize this picture. Yeah. So now of course there's an isomorphism that I haven't written down anymore. Yeah. So this is something we have to prove. So we need stuff like this. So if I'm going to other types, I'm going to other Lie algebras, I need to find a tau such that there's an isomorphism. This is the first thing. Then I need to find this identification of lambda to lambda triple. This is the second one. I need to prove the theorem for fundamentals, but we can always deal with fundamentals. And then to make this all work, I need to have a Minkowski property. So now I have to find the situation where this actually works. So as I said, we have cases where we have a Minkowski property. Even in the orthogonal case by Igor, this has a Minkowski property. That's enough. So as long as I just have to prove, so here maybe fundamentals or let's say finitely many examples. Yeah, that's enough. As long as it's finitely many, you can just do it. Yeah. And Igor is telling us, yeah, okay, fundamentals don't work, but you have to take 2 omega n. So it's still finitely many. So I actually really have to prove the theorem for fundamentals or these finitely many, the generators of my semigroup. And I need the Minkowski property. And that's it. Then I'm done. So the point is now, yeah, I have to find tau. And it's not only finding tau, I actually have to find the Lie algebra first, and then I have to find tau. And it's not only finding like a collection of commuting roots, but this lambda to lambda triangle has to be compatible. So the scalar products from G, the non-abelian version, has to be translated to the scalar products in G tau. So between your roots and your lambda, the scalar product has to be find also in G tau with some beta and lambda triple. So it's a combinatorial problem. It's a combinatorial problem that you want to find something that is abelian or as abelian as possible, and has the correct scalar product. Yeah, so it's a combinatorial problem now, whenever you have a Minkowski property. Now, let's go back to our cases where we have a Minkowski property, namely, we have it for SLN. Yeah. Then I said, so this is the paper with Rocco Kirivi and Xin-Fang. We consider the Demasur for type SLN. Yeah. So as I said, for triangular elements, we have a very nice Minkowski property, so we have the Minkowski property. Unfortunately, now you have to find your tau. You have to find the correct configurations. And this is not as easy. Namely, if you consider Demasur modus, as I said, so we have here the triangular elements translated into, if you prefer, let's say a symmetric group description, then these are pattern avoiding. Yeah, so pattern avoiding, it should be 4-2-3-1 and 2-4-3-1 avoiding, which actually means, so this means that if you take this one and your Y group element spits out this, then this is forbidden, or this. But pattern avoiding means 1, 2, 3, 4 can be any 4 numbers, increasing numbers, and the configuration should not be this. So these are triangular elements. And then we have as I described, the face of the polytope gives a basis for the Demasur model. Actually, this triangular element, why is this triangular? Because it's a configuration in the following way. So you have to consider this set here as sitting inside my SLN picture. Yeah, this lower triangular. And if you have beta 1 and beta 2 in your, if you have beta 1 and beta 2 mapped to images, being images of, so omega. Yeah, so suppose beta 1 and beta 2 are in this set, then also the union and the joint has to, the union and the cut has to be in this set. Yeah, whenever this exists. Yeah, because whenever this exists, this is triangular, and unfortunately for these sets we have a nice basis. But now it comes this combinatorial game of finding the right scalar product between roots, and it turns out it doesn't work for triangular elements. Yeah, but we can make a restriction, namely we call it rectangular elements, and rectangular elements are triangular elements where also these two patterns are avoided. Yeah, so this is like I have to also avoid these two patterns, and it's basically saying like if you're in such a configuration, and you have beta, so you have a beta 1 and beta 2, and suppose these two elements are in your set, then beta 1 and beta 2 are also in. And whenever you have such a configuration, then whenever you have a rectangular element, then you find an appropriate tau. So your element W is some rectangular element, then you find an appropriate tau such that you can apply the construction that I just presented.
Ghislain, I'm sorry.
Yeah.
Why do you call them rectangular?
Oh, because now it's a rectangle, not a triangle anymore. Yeah, because in some sense the triangle elements were actually saying that so you have these two, and they have to form a triangle, and this one here is not necessary. It doesn't exist necessarily. Sometimes it doesn't exist. Yeah, and rectangle means whenever you have these two, you also need these two. Yeah, so whenever you have these two, you also need these two. So they form not a triangle anymore, but a rectangle. Yeah, whether this is a useful name, I don't know, but it's like the pattern is is this one. Of course, you could also say like these are the following avoiding sets, and actually it turns out that if you search for triangular elements and you start computing the first one, you find the sequence in integer sequences, and then integer sequences are spitting you out, oh, this is this pattern avoiding set. Yeah, and the same for rectangular elements, it's just an integer sequence. Unfortunately, the number of triangular elements compared to n factorial is small, and the number of rectangular elements is even smaller. Yeah, so we are not covering a lot. It's here, maybe you want to correct me, but I think for S4, so you have 24 Y group elements, then 22 are triangular and 20 are rectangular. This sounds like really a lot, but if you increase n, then this basically the quotient goes to 0. So there's nothing much, not much left. Yeah. Okay, so so this works. So we have a pattern where this actually works. Now this is now a paper with Rocco and Hin, and here's what we did so far in the future. Let's consider type B. Namely, type B, we're considering the basis. We need some basis. This is one ingredient in the theory, and the basis is from Igor. But Igor already wrote in his paper, yeah, that's not a PBW degeneration, because I have to give all the short roots degree 1/2, and all the long roots get degree 1. So it's not abelian. Or maybe you give all short roots degree 1 and the long roots degree 2, but it's not abelian. Yeah, this is what he already wrote in his paper. But here's the story. So let's consider this tau 4. Yeah, so this tau 4. Yeah. We have to see now. If you look at this, you know how to generalize to tau n. Yeah, so you 1, 3, 2, 4, 5, 3. Then you have the last one. They are twiddled, and then you're going backwards. Yeah, so this is tau n, and so now this is one thing. So we have to understand we want to twist everything. We want to consider the positive roots. So if you take tau 3 inverse on phi plus intersect with phi minus. So I'm just taking this tau 3 so I can draw it. This is this set of roots inside B, and now be careful, this is now inside B5. Yeah, I'm starting with B3, yeah, and I want to go into B5, and this is the set of roots. And you see immediately there's something strange, because this is not abelian. It looks like the configuration as before, but it's not abelian, because you see immediately that if you consider the commutator of these two, then it's this. Yeah, and the commutator of these two is this, yeah, and so on. So what's the statement? The short roots are not commutative, because you can only take commutators in these short roots. So this actually matches exactly Igor's note in his paper that the short roots are not commutative. So here's a Y group element, and whatever you can do, so you have the correct set of roots. Yeah, you have the correct Y group element. You make the assignment omega I goes to omega 2i minus 1. and then you have an isomorphism, because then everything else applies. So again, here's your you check that your scalar product work, and that for fundamentals you have to prove it by hand, and the rest you get from Igor for free because you proved the Minkowski property already. So in this setup, you could find the degenerate, the almost PBW-degenerate module as a de Mazur module in B5. Yeah. Okay, so let's look another example. Yeah, because this is type B. So now type D is a little bit problematic because Igor hasn't written this up for type D, but only for type B. Yeah, so we have some idea how to put this into type D. Yeah. But let's do another type, because for my list in the beginning, there's one type missing. Yeah, so I have to say the theorem by Cerulli, Irelli, Lanini, and Littmann also applies for symplectic. Yeah, the symplectic is fine. Yeah, it works in the very same way as before. But here's another funny example, namely there's also G2. In G2 we have a basis given by Gornitsky. Yeah, and I'm considering the following Y group element, namely I'm considering this Y group element. Now there's a 0, and 0 means this has to be something affine. And yeah, this is a Y group element on D43. Yeah, this is my Dünken diagram here, and this is my Dünken diagram here. And now I wrote down, if you take this Y group element, yeah, then the set that you're getting here, yeah, so this set here is exactly this one, and then you see a very nice matching between these two sets, and again it works. Yeah, so again you have the right scalar products, but and again it's not abelian. Yeah, it's not abelian because what I have to do is I have to give the highest root degree 2, because the commutator of two roots that give you in the commutator the highest root is not 0. Yeah, so this is why all roots have degree 1, but the highest root has degree 2. So it's all again almost abelian. So what is special here? The basis by Gornitsky, he doesn't say something like this. He's talking about essential signatures and just providing a basis. But giving the highest root degree 2 doesn't hurt, because for fundamentals, the highest root can have degree 2 and it's still a basis, whatever he provides. It's still a homogeneous basis. Yeah. So his Minkowski property, together with this choice of Y group element, actually gives you again the isomorphism that we were asking for, namely this one. Yeah. Again, this A is almost abelian, so it might be a double A here, and it's the Lie algebra is again not abelian; it's almost abelian. Okay, so now you see why is this example particularly nice? Because you see, yeah, you can find this, but maybe you have to go affine. Yeah, because there's, in some sense, the philosophy is you have your Lie algebra, yeah, you have your roots, and you want to make them abelian. Yeah, so you want to make them abelian, and you see from the SLN case how to make them abelian. You just split them. Yeah, so alpha 1, 2, 3 goes into alpha 1, alpha 3, alpha 5. So you just stretch this, and you can stretch, of course, in this infinite series. You can always stretch from AN to A2n-1, from Cn to C2n-1, Bn, Dn the same. But in the exceptional types, you cannot stretch. There is no space. There is no G2 which is stretched. So the G2 which is stretched is in D43. Or actually, you could also use G2 affine. Yeah. So I was computing the example with D43, but actually it also worked with G2 affine. Yeah. So then you see, yeah, there's enough stretch because there's enough space to make everything abelian that you want to have abelian. Okay, so now you since the G2 picture works, now where to look for F4? You have to look for an affine Dünken diagram where you have F4 inside, and this is E6 too. Yeah, and then you have to look for, and that's getting a little bit complicated, and we haven't done this yet. E6, 7, and 8. Yeah, it's not clear where to find them. Yeah, because there's not enough space to stretch. Then I have to say the following: this you see in the G2 case, it's not abelianized, and there's actually Rocco actually proved this. So now I can't find it probably, but he has just a list saying like you cannot put Bn for n greater equal to 3 into some abelianized into a Schubert variety. You cannot do this for G2, you cannot do this for F4, and you cannot do this for E6. Yeah, because there's some root combinatorics that he used to explain this. Yeah, if he's in the audience, maybe he can say a word on this later. Yeah, but you see, this idea of yeah, let's find this degenerate module in a Lie theoretic setup again works when you consider affine root system. So now actually, so now you know how to proceed. I mean, yeah, so there's like there is D missing, yeah, but as I said, we just need the appropriate basis. And then the problem with F4 and the type E cases is not only that you need to find the appropriate Weingroup element, yeah, and the combinatorics of scalar products should work, but I mean, there's no Minkowski property because we don't have a basis. Yeah, so whenever you have a basis, you should go look for an appropriate Weingroup element. But as long as you don't have a basis, there's the one ingredient in the proof won't work. Yeah, and so as long as we do not have an appropriate basis for F4, this particular proof will not work. And so now, what is the nice thing here? Of course, I said in the beginning in the title there's some variety going on, but now this is all you need to get your varieties. Yeah, because yeah, so if you talk about varieties, then the flag variety is just defined as some highest weight orbit. Yeah, so we just define it here as a highest weight orbit. The degenerate variety is again a highest weight orbit, yeah, because you abelianize your group, and then there's a corresponding algebraic group, and then the degenerate variety is sitting inside this VA lambda, and on the other side, you know, there's an isomorphism. On the other side, you have the Schubert variety sitting inside the projective space of the Dimarzot module. But then on the open cell, they are just isomorphic, yeah, just because this isomorphism is actually all what we just did, yeah. So you have this U gamma, these are the commuting subgroups, and U beta, this is the abelianized subgroups, yeah. So you have this isomorphism, so this is why you get this one here, yeah. And the good thing is there are two things. You have this is a Schubert variety, so it has nice properties, and this translates into this degenerate variety. Of course, you don't need all this to deduce these nice properties, because this is basically what is already in our favorable module paper, that you can deduce these nice properties. As long as you have the Minkowski property, you can deduce this immediately. What is here for free actually in this construction of the Dimarzot module is isomorphic to the degenerate module. For Dimarzot module, as I said, is you have defining relations. You get defining relation for your degenerate module for free. Yeah, because they're just the defining relation for the Dimarzot module. Yeah, so I don't know, Igor, maybe you can comment on this, because in your paper there are no defining relations for the degenerate module. Maybe they just pop out from here, or you just get them from this Dimarzot construction here. Yeah, so the defining ideal that I explained in the beginning for SLN and SPN, you get the very similar defining idea for the degenerate module also in type B. You get it in type G, or wherever you can apply this entire machinery. So this is basically saying you need some kind of Minkowski property for finitely many modules. You have to prove everything for these finitely many modules, and you have to find the appropriate Weingroup element in some larger, in some Lie algebra of larger rank. And then you can apply all this and identify your degenerate module with a de Morseau module. And in some sense, it's like in the BN case, this is the statement that also is hidden in here. You cannot degenerate further if you want to have a Schubert variety. There is no way you cannot abelianize everything if you still want a Schubert variety in, let's say, a natural way. It might be that somehow this is a Schubert variety, but in a very natural way, this will not be a Schubert variety. The same for G2. You will not find a Schubert variety where the global section, the de Morseau mods, are exactly your degenerate module. Yeah, so the just root combinatorics are telling you you can't do this, and this is as far as you can do. Yeah, so this is as far as you can go if you want to still have a Schubert variety. Yeah, so this is like on one side you can ask, so I want to have that you can consider the abelian the abelianized modules and try to understand them. Yeah, so you just abelianize and try to understand the module, or you ask, so how far can I abelianize, how far can I degenerate such that this is still the de Morseau module? And as I said in the very beginning, in the type A, all of this is just the same because type A is so well behaved that everything is nice. Yeah, but outside of type A, suddenly these are two different things. So there is an abelian degeneration and there's a Schubert degeneration, and these are two different different things. Okay, so I think I'm done. So I don't want to talk about toric degeneration. So I just want to talk about PBW degeneration. So never mind toric degenerations. This would be, of course, the immediately implied by all these polytopes. Yeah, but yeah, that's all I wanted to tell you.
Thank you very much, Ghislain. Are there any questions, comments, remarks?
Okay, so I wanted just to make two brief comments. So concerning type D, well, I just wanted to say that I have no idea how this is done, how anything like this is done in type D. I tried for quite a while, but I didn't come up with anything. So if you guys actually know something that could work there, that would be just. You just said it. I didn't write it down. Well, I didn't write it down because I actually have no idea what to write.
Okay. No, but yeah. So we focus on type B to get the matching. But then we discuss something in type D. So actually, we already have the Weigub element for type D. Yeah. So it's like we have the Weigub element that actually should give you the right thing. Yeah, again, it's not completely abelianized. Yeah,
so you have the subalgebra.
Exactly, there will be whatever. So in Bn, this is these short roots, and now you have to translate these short roots into Dn. All roots have the same length, but you basically blow them up, yeah, into pairs of roots, and they are not abelian then. Yeah. Okay. So we had the Weigub element, but yeah. So yeah. Think we had maybe you correct me, but we had this idea how to do Dn, but maybe you can't. Maybe you also can't remember, yeah.
Okay, so I can't remember exactly, but we thought this might be related to the matrix presentation because there's all SO blah blah to SO blah blah.
Yes, this is Rocco. Yes, I think the same. I don't remember, but I think B and D from the combinatorial point of view are similar, are very similar. I do remember playing this kind of game also another time with my friend Andrea Maffei, maybe you know, when we studied the symmetric variety and realized them as open, some kind of open set of fine Schubert varieties, and the game was similar. You have to enlarge somehow the Dinking diagram, and also there B and D were difficult, and C and A were easier, And also, but I'm talking only about the combinatorial side. I would also add another remark. One can play this game in the other side. One can say, consider this sub-diagram or this thinking diagram, and then you make some roots commutative and some other no. Maybe they are not interested in the subset you are making commutative. But for example, for G2, I do remember that we have different way of realizing this. Making different subsets of roots commutative, and we have some kind of uniform recipe of how to construct the enlarged thinking diagram, but only partial. It looks like it's a very special case when everything works, and one has not to expect that all the roots become commutative.
Yeah, exactly. So we have, as I said, so there's a D43, and you can also put this into G21.
Yeah,
But
G21, yes, you already said it. Yes, thank you.
Yeah. Yeah, Igor, you had 2 comments.
Oh, no, I just wanted, I think I can answer Evgeny's question. So I think for SLN, for de Mazur models, I think there is, so an example when lambda, so when the Cartan component for 2 isomorphic PBW degenerations is not for lambda is not the PBW degeneration for 2 lambda. So
Okay.
if that's what you were asking, I think there is a counterexample.
Oh yeah, can you send me the counterexample? So for the S in the notion lambda is equal to mu. Yeah. Or
So
is it in your paper? And
well, it's not in this form, but I think I can put it into the chat. I think so. You should take so the highest, so lambda should be lambda should be this. So this is, and then W is equal. So 2, 5, 3, 1, 6, 2, 5, 3, 1.
You mean SL6 or what? SL6.
SL6, yes. So so this is similar to the example in my paper, but if you look at it, if you take now 2 lambda, then it decomposes into 2, 1, 0, 1, 1 and 0, 1, 0, 1, 1. So, well, it's sort of, I mean, it's not very easy to explain verbally, but but then so you decompose it into 2 multiples, and then you decompose one of them into 2 more multiples, and then so you use that, and then so you have 3 multiples, and for the first 2 you do have an isomorphism, and for the second 2 you do not have an isomorphism. So altogether the map is actually is essentially surjective. So there is a kernel, and so there is a kernel. I think it should work, but of course it needs to be double checked.
Okay. Okay, yeah, maybe, yeah. But it's a good example, yeah. Okay.
Further comments, questions? Okay, if not, let's thank Ghislain again. Ghislain, thank you very much.
Thank you.
Thank you. Okay, let me stop the recording.